everyone. Good afternoon. Here we are with another webinar for better understanding on the cathodic protection in effective corrosion control strategies. Before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, if you would introduce yourself, your name, designation, company, and the country you are based in, we would be in a better position to know your background. It's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. We are getting your replies, and thank you so much for confirming. I would like to thank you all for registering and taking time out on a Sunday to learn about the role of cathodic protection in effective corrosion control strategies. My name is 𝐊𝐞𝐲 and I will be your introductory speaker for today. It's our pleasure to host this webinar for you. This is our 93rd webinar in a series of technical webinars that we are conducting every month. As a practice, we conduct one webinar every month. So please follow us on LinkedIn and YouTube to make sure that you are updated about our latest updates. Today, we have an experienced panel of speakers. I am with my colleague, Mr. 𝐊𝐞𝐲, who's Managing Director, Principal Integrity and Safety Consultant, Madam Mobina Khatun, she's Director, Engineering Services, and Mr. Tony Williams, who's General Manager, Global Sales. Moving forward, during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on the topic, and you can type your queries in the question and answer window, and we will try to respond you in question and answer window, or we can take your answer live. We will try to answer as many questions as possible during this session, but as we have a detailed question and answer session after the completion of the topic, please accept our apologies if your question is left unaddressed due to high volume of queries we generally receive. Furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussion through question and answers. Before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those around us. Since this is a quite technical subject, we will touch only the key theoretical aspects of role of cathodic protection in effective corrosion control strategies. In this limited time of 2 hours, we request you all to follow us along with asking questions to help us make this session as engaging as possible. So let us begin, and I will start by giving a brief introduction about Velosi and what we do. Velosi is a leading global consultancy firm that provides asset integrity management, HSE, engineering, environmental, and software solutions to the clients in the oil and gas, energy, power, and petrochemical industries around the world. We also have our in-house proprietary software, VAIL-Plant, which is an industry-leading SAP-certified complete asset integrity software solution currently being utilized by energy giants like ADNOC, Dragon Oil, BSR, TANAP, and many more. Founded in 1982 in Malaysia, Velosi Group was then acquired by Apple Spain in 2011 with above 42 years of experience. We have expanded our footprints in more than 86 countries worldwide. We have so far completed more than 1,350 projects, and many projects are in line and have served more than 500 clients so far. By combining global coverage and local knowledge with our wide range of services, we create tailored solutions to complex problems. Our range of interrelated services and integrated approach ensures that we can accommodate a wide range of projects.
Good day and Assalamu alaikum everyone. Today's topic is very common. I was checking the social media. There are many presentations available, and at the time of topic selection last time when I was discussing with our colleagues, team members who work on these webinars, so I was advised like one difference what Velosi makes is the issuance of the attendance certificate. Like whoever would be attending this webinar, he would be given attendance certificate. Number two, the content of our presentation, we try to make more comprehensive, and timing wise, we try to take 2 hours minimum, so as we can deliver reasonable material to all attendees, whether you are a young engineer or experienced person. So what we try to focus, you would be able to get some information regarding applicable standards. Then we also present the background of how this technology evolved, and then case studies, and then software part in this case. So the software what we'll be presenting, that is a CPMS, CP management system, and the calculation part of the software that is not presented today. And as my own like a background is as a process and corrosion engineer. I'm not 100% a CP specialist. So I would be supported by my colleague, Mr. Abdullah from Pakistan. So he would be helping me as the any like a more detail would be required to be added. As such, if I can explain like a background of the CP system, like my own learning came from background. Like sometime I heard that corrosion engineer working on the pipeline. And when we see the CV, we find that he's working on the cathodic protection. And as a process corrosion engineer, we don't consider like a CP engineer as a corrosion engineer. CP engineer is a CP engineer, right? And cathodic protection does not provide solution for all kind of industrial corrosion problem in oil and gas sector, in refining sector, or petrochemical sector. In general, like there are mechanisms where we select material of construction properly as per the service of the facilities or the plant or the equipment and the composition, operating conditions. So somewhere we use carbon steel, somewhere we use CRA material, somewhere where we use cladded equipment, and somewhere ceramic and somewhere lining, and somewhere coating, internal, external. So the point is like how we differentiate where cathodic protection comes in. So as a normal process engineer, as a layman, I will say the CP normally used for the buried pipelines, buried steel structures, under the sea structures, under the sea pipelines. And somewhere, some areas, people are also using internal CP to prevent internal corrosion of the basically equipment. For example, tanks internal corrosion can be protected. Some separators, anodes are like sacrificial anodes are installed, and in some big tanks, CP like impressed current cathodic protection, what we called ICCP, is also used. So the main purpose is like if like I will be covering step by step, but for cathodic protection, we need like we called various like a minimum requirement, like we need to have a anode, we need to have a cathode, we need to have a electrolyte, we need to have a connector. ACME is a word. ACME, like 4 ACME elements are required to make a cathodic protection effective for any structure which we need to prevent from corrosion. So in general, CP is which is being known in the industry for the underground pipelines, for the underground other structures. It can be used for the concrete bars, but provided connections are provided properly to the bars. Then subsea structure, subsea pipeline, or internal, they're simplified. Then other areas, the CP is not being implemented that much. So starting with that, we need to understand like the corrosion mechanism and challenges. Like if all of you or most of you might have heard that like there's API 571, API there's a NACE standards, and there are also other ASTM corrosion related. So in API 571, around 67 damage mechanisms are there. Under ASME B31.8S in pipeline, there are 22 threats, which covers internal, external corrosions, fabrication related issues, operational issues. So, however, there are 32 addresses. There are threats which are required to be managed as a part of integrity management of the pipeline. So now, when we see in normal, what is a corrosion mechanism in simple terms, like we all know that mostly these pipes are made of carbon steel or steel, normal carbon steel, and in steel, major component is Fe, iron. Iron can combine with oxygen, can make ferrous oxide, and ferrous oxide is a rust. And in general, due to that normal phenomena taking place, like here, why CP is important, why corrosion management is important. So it is considered in terms of dollar value. So in the world in 2011, the number what we got from the other sources is $2.2 trillion are being spent on the corrosion prevention. So it is a big amount, and it means that it's very important the corrosion protection should be done effectively. Like what are the various type of corrosions? So one of the most exhaustive corrosion is external corrosion. There is internal corrosion, as I said, various aspects which are coming from the a process related, operation related, temperature related, composition related, and there could be third party aspects as well. So the major one is external, which is normally protected by CP. So this one is one of the biggest threat. If you see from the top, it's the second one, external corrosion. The Pipeline Research Committee, international PRCI, has classified the 22 root causes for a potential integrity threat on any pipeline. USA discovered the second most potential to the pipeline failure is external corrosion. Here, if you see UK Onshore Pipeline Association study comprising on 21,000 kilometers of liquid and gas pipeline, most of which is in dry gas. So the major threat is also shown as external one, if you see here, 30%. So major cause of the failure are external interference and the external corrosion. So here also, if we see the corrosion, green, is also becoming one of the major aspect, and similarly corrosion and other damages as well. So when we go that external corrosion, how that corrosion aspect is being managed, right? So here normally there is a carbon steel is a mixture of ferrous or Fe, carbon steel, silicon, or the other component which are made to make the carbon steel as per section 2. Then there could be iron which could combine with oxygen in the presence of CO2, H2O, and then some energy is released and converted into Fe2O3. It is called hematite as well, iron ore. And this is the original shape of the steel, the ferrous as well. When we normally try to take out iron from the ores, it is Fe2O3, right? Then when we heat it up, by heating, energy added, heat, and then Fe is generated. And then by mixing of the various compositions, we try to prepare the ferrous or a carbon steel, as we normally call it. So here, when a carbon steel is exposed to oxidizing agent such as H2O and O2, it releases stored energy and transforms into Fe2O3. Hematite and rust share the same composition, and Fe2O3, as a steel rust, it releases latent energy, stabilizing back to oxidizing form. So it means the rusting of the steel is a natural process. So unless and until it would be prevented, it can continue and it can cause the damage to the equipment. As a normal process, what I'm just trying to see that how the iron is produced and how iron is converted back to the same kind of rust is the same process, iron oxide taken from the ore, blast furnace, then Bessemer, and this way a steel pipe is made. But then the same pipe, when corroding, it converts into iron oxide back. And this is the process what we need to prevent. Here is a small video which is showing that it came from ExxonMobil, and if we can open the
Rusting
sound.
of steel is one of the most common examples of corrosion, and yet surprisingly little is known about how steel corrodes at the microscopic level. This time-lapse video shows a flat plate of steel corroding over the course of a day in the atmosphere next to the sea. Although the surface never actually gets wet, corrosion can be seen to start at small spots. As time progresses, the rusted areas extend
It is
gradually in
a
a
1 to 2
filamentary
minute
manner,
video just
often
showing
following the direction of the grinding marks. This is known as filiform corrosion and more usually occurs underneath paints and coatings. The head of the filament contains corrosive fluid or electrolyte which forms after sea salts fall onto the metal surface during the atmospheric exposure. Sea salt mainly consists of sodium chloride, which dries as cubic crystals. Some salt deposits can be seen as small squares on the rust after the exposure. The corroded parts of the steel are the anodes, where the anodic reaction, metal dissolution and rust formation, has occurred. Perhaps surprisingly, some areas of the steel have remained uncorroded during the 24 hours of exposure. These areas are the cathodes, where the cathodic reaction, oxygen reduction, has been occurring. Since no metal is corroded in these areas, the steel remains shiny. During the process of corrosion, anodes and cathodes move around until eventually, after a sufficiently long period of exposure, the whole of the surface will be covered in iron oxide corrosion product. This is a good example of how anodes and cathodes are as distinctive as the opposite ends of a battery and must occur at different locations on a corroding metal. Let's look at the movie again.
So here, what we try to see that in this corrosion process, one cathode and one anode, where corrosion is taking place, that is the anode. For example, normal, it is the oxidation process. Fe is combining with oxygen. From the chemistry point of view, from the cell number 2 or 3, the Fe comes and oxygen comes from the cell number 6 from the table. Then from this table, if you see that Fe is losing 2 electron or 3 electron, and then combining those 2 electrons are being given to oxygen, and oxygen is combining with Fe iron, and to make the equation Fe2O3 is being made, right? So it means Fe is losing 3 electrons each, and 2 molecule and oxygen getting those 6. Each oxygen get 2 electrons, and this way Fe2O3 is being made. Simple. If we try to see, in this process, the important thing is how this process take place. Even for a steel, if a normal steel lying in a dry area, we have seen, I have personally visited Algeria desert, where the rain is very seldom. So we have seen pipelines lying out in the desert, no corrosion whatsoever, because there is no water, it's dry. It means that unless and until there is a water or electrolyte, what we call it, the corrosion process cannot take place. We're talking about wet corrosion, we're not talking about high temperature or other mechanism where other corrosive element comes, but we're talking about wet corrosion environment, which what we're focusing as an external corrosion caused by environmental corrosion. So here, if we see normal laboratory, here if we see magnesium is one anode, and there is a steel as another cathode. So here there is electrolyte, and then there is a metal path. So here ions move basically in the electrolyte, and electron goes from magnesium to steel. Steel lose electron first, but the same electron is being compensated by magnesium. So normally, if we say in cathodic protection, there are 2 type of basically players which are playing the role. One is like anode, other one is cathode. Anode is depleting and cathode is basically beneficiary. In normal, there are 2 type of CP. One is like ICCP, like impressed current cathodic protection, which we don't see the name, but here also anode is sacrificing. But we have another type of CP which is called sacrificial anode, mean anode which is sacrificing itself for the sake of cathode protection or enlarging the life. So the galvanic type. So this is the basic process. Like electrochemical reaction involve electron transfer during corrosion. Electron and ions move freely, creating an electrical circuit known as an electrochemical corrosion cell. This figure shows that such a cell between magnesium and steel called a galvanic corrosion cell. 2 dissimilar metals are connected with a copper wire and placed in salt water. Magnesium, having a more negative potential, becomes the anode, while steel with a lesser negative potential act as a cathode. So what is the equation here? Manganese is losing 2 electrons, and those 2 electrons are taken by steel because steel is losing those 2 electrons as a part of oxidation process. So in this process, a chemical reaction at the magnesium anode is called an anodic half cell reaction. Figure is a magnified view of the anodic half cell reaction. When the metal corrodes, metal atoms lose electrons and go into electrolyte as a positively charged metal ions. This is shown in this item. Now, the reaction above is an example of oxidation. Oxidation is a chemical reaction where electrons are lost. The 2 electrons are left behind in the metal when each magnesium ion goes into the electrolyte. The loss of metal into the electrolyte is characteristic of the corrosion of an anode. This is normal process which happens. So here like cathodic protection, like a half cell reaction. Here, electrons that are produced in the anode half cell reaction flow through the metal path to the cathode. At the cathode, the electrons are used in a chemical reaction. The chemical reaction at the cathode is called cathodic half cell reaction. This one shows a reaction that occurs at the cathode in acidic solution. Hydrogen ion from the acid solution use electron from the cathode to form hydrogen atom. The two hydrogen atoms usually combine to form one molecule, this process. So electrons that are produced in the anodic half cell reaction flow through the metal path to the cathode. At the cathode, the electrons are used in a chemical reaction. The chemical reaction at the cathode is called a cathodic half cell reaction. This figure shows reaction that occur at the cathode in acid solution. Hydrogen ion from the acid solution use electron from the cathode to form hydrogen atoms. Two hydrogen atoms usually combine to make the hydrogen molecule. So overall, if you see, like water atom at a cathode, reduction reaction take place, which two hydrogen atoms and OH atoms are produced. Now the oxygen and H make water, and oxygen and H2O then combine again for 4H, and in this process the oxygen and water are present. The cathodic reaction of the Corrosion are different. In this case, the Corrosion occur about 100 times faster than the absence of the oxygen. Here at the end, what we see, 4FeOH combine with oxygen to make Fe2O3 and water. This is the resting position. Like if we see equation combining first two equations, Fe combined with OH, Fe combined with oxygen and water, and then FeOH, and then these, when we combine FeOH with O2, Fe2O3, that's why water become important. If water is not there, this reaction will not be facilitated. Here, like a simple method, if we try to understand as a layman, like distinguish between electrodes, one is anode, another one is cathode. Anode and oxidation both start with vowels, right? Whereas cathode and reduction both start with constant, like not non-vowels. So it means that like anode undergoes corrosion, whereas cathodes do not corrode basically. This is the objective of CP system. Anode undergo corrosion, cathode do not corrode. The process of converting anode to cathode is known as cathodic protection. Here you can see that also the same example which I gave in the beginning, ACME. ACME means anode, C cathode, M metallic path, and E electrolyte. Here if you see this is the electrolyte, and this one is a metallic path. Here is the anode and here is the cathode, and this is depleting and this would be building. This is a normal process. Here, like anode, cathode, and metallic path is typically inherent in a metallic structure. As soon as it is exposed to the electrolyte such as moisture or water, corrosion process start automatically. Without an electrolyte, there is no corrosion, but this is not possible on like people say there would be some kind of water available, so corrosion would be taking place, but there are areas where there is a dry area. Anyway, the direction of current flow is important in the corrosion process. The electrons flows from the anode to the cathode through the metal path. It means a wire connection is required, while electric current flows from the anode into the electrolyte toward the cathode and back to anode to complete the cycle. Notice that current flows through both the electrolyte and the metal path. Electron flows only through the metal path. Now, if we see that as Ohm's law, anode basically is the loser. It would be depleting. It is not a charge-wise. Charge-wise, anode is always positive, cathode is negative, electron being added to the cathode. But this one is only with reference to the weight. Like anode always on the loser side and cathode always gaining side. According to Ohm's law, the corrosion current increase as the potential difference between the anode and cathode increase. The following two factors influence this potential difference: dissimilar metals, dissimilar electrolytes. Here, When we say two dissimilar metals, for example, here when two dissimilar metals are electrically connected in an electrolyte, the difference in their potential will cause current to flow. Greater the difference in the potential, the greater the current flow and rate of corrosion. Like here is a list of the metal arranged according to their potential in a specific electrolyte. The galvanic series is used to predict the galvanic behavior of the metal that are electrically connected in a neutral soil or water. For example, if a magnesium and steel are connected in a soil or water, the magnesium would corrode and the steel would not corrode. Later, we will apply this principle to cathodically protected steel with the magnesium anode. Here, this is the potential like coke graphite plus 30, and if you see magnesium alloy AI zinc minimum minus 1.55, this is the copper sulfate potential, and high potential magnesium alloys even 1.80. Normal steel excuse me, with mill scale is 0.20 only. So this number for your but what a noble and non-noble metallic part we will be using as a anode and cathode. Noble mean which is we want to protect, non-noble mean which can be used as a sacrificing party. Here, if you see this, like if a steel tank floor, then there's sand, there's a copper ground. So this potential, like how this electron will flow from this anode to this cathode. So this is one example. Then the dissimilar metal like a brass and steel pipe are galvanically coupling. If they're connected together, then there could also be a flow of electron from the high potential to low potential. So one of them would be acting as a anode, other one would be acting as a cathode. That's why galvanic corrosion can take place in these kind of scenarios. Similarly, dissimilar metal, new and old steel pipes are in galvanic coupling. That may also cause some kind of corrosion. So it's not only the phenomena is being applied for the protection of the corrosion, the same phenomena may also cause galvanic corrosion. So corrosion engineer need to be basically active and watching it when they are making these kind of configurations in the designing stage of the equipment. Here, if we see anode and cathode relationship between metals, for example, anode wise, if this is the anode and this is the cathode, you can see what is the potential difference. For example, mild steel new and mild steel old. This is 0.70 and 0.50. Similarly, if we take magnesium alloy, it is a minus 1.75 versus steel 0.5. It means that this can work as a cathode, anode, and this item can work as a cathode. So dissimilar electrolytes also, if you see that like when a pipeline passing through areas, so there could be various kind of soils, there could be a marshy area, there could be a desert, there could be a like a river, there could be some mountains. So all these areas are having different kind of basically conditions, and each condition may have a different resistivity. So the soil resistivity along the path of a pipeline is very important, and that path is basically helping us to estimate how much resistance would be there, how much volt potential is required to transfer the required current to maintain the equilibrium of the electrons. So that is important to know, and this is one of the important activity while designing the CP system. Here, if we can see that like when pipeline is passing by, like here pipeline in a dissimilar electrolyte, dissolved salt concentration, then pipeline in a dissimilar electrolyte, dry and wet soil, and then here pipeline in dissimilar temperature electrolyte, thermal cells. So all these aspects are required to be considered while selecting the CP system and designing the CP system and the anode sizes and the volume of the TR units, etc. Next, for example, if there is a vertical, for example, well casing for the anode, then the electrolyte from the top to bottom of the anode, when it is being basically buried in the soil, so it may have a different conformations and different kind of basically relationships with the reference to the resistivity of soil and from the top to bottom. So accordingly, we need to assess like how much optimum resistance would be there and what maximum voltage potential is required to maintain that electron flows. So well casing exposed to different electrolyte compositions, and that has to be considered. This is one of the vertical like anode, and this is a horizontal. For example, pipeline dissimilar electrolyte dissolved in salt concentration when we have like anodes in the parallel to the pipeline. So if we go like this is up to this time, we covered like a normal Corrosion mechanism, how the theory-wise CP is connected with normal oxidation process, and what is the role of electrolyte, what is acme, right? And now like main two standards what we want to cover. There are other standards as well, but like the main standard which is like being used as a like a basis for the CP system is ISO 15589-1. It is a petroleum and petrochemical natural gas industries cathodic protection of pipeline systems like on-land pipelines. Then NACE SP0169-2007. It is a control of external corrosion on underground or the submerged metallic piping systems. So when we see ISO 15589-1, so it covers complete details like for sizing and designing of the CP systems. If I can quickly go through the topics like CP personal competence, then cathodic protection criteria, prerequisite for the application of cathodic protection, then lightning and over voltage protection, coating, the selection of the pipe trench backfill material, and the equipment for the reduction of AC interference, equipment for the mitigation of DC interference. Next, if we like more details are there. If we see the standard, like it provide you all help what you need to design a CP system, like basic requirement of cathodic protection design. I'm not going further detail. Impress current stations, then galvanic anode system, monitoring the CP system facilities, then like commissioning of the CP system, monitoring and inspection and maintenance of the CP system, then documentation. So if you see this, like I would like highlight people who are raising the hand for the questions. Please write your question in Q&A window, not chat window, and there would be two like a question answer sessions, one in the middle of the presentation, other one would be at the end. So we'll be answering these questions. So please keep writing your questions in the Q&A window, and we will be answering those. So scope of the standard is applies to cathodic protection system for on-land pipeline in petroleum, petrochemical, and natural gas sector. Cover design, installation, operation, and maintenance of both new and existing pipelines. Purpose and objective: prevent corrosion, extend pipeline service life, enhance safety, reliability, and regulatory compliance, provide engineering guidance for effective CP system implementation, and like keep up to date. So next standard, then in NACE there are various standards, but we are only showing SP0169. In this standard, the similar details are available as 15589. So here, like determine of the need of external corrosion control, piping system design, external coating, criteria and other consideration for CP, design of cathodic protection system, installation of CP system, control of interference current, then operation and maintenance of CP system, then external corrosion control records. So this standard also available, so it should be use that as a reference. Next, too many points are there. How to like upper layer I need to remove. Okay, now guide basically if you see that NACE SP0169, the scope of the standard guideline for controlling external corrosion on underground or submerged metallic pipelines, applicable to new and existing installation across the various industries. Purpose same: prevent and mitigate corrosion risks, enhance pipeline integrity and safety, provide practical design, installation, and maintenance recommendation, promote consistent industry-wide corrosion protection practice. Here, if we try to see here, is a guideline for controlling external corrosion underground or submerged metallic pipeline. This point is very, very important for the newcomer to remember. CP system cannot be basically installed on like everything. This is more effective if the line is underground or structure is underground or submerged in the water, because for CP system to work effectively, electrolyte is required. If electrolyte is not required, it cannot work. It means that CP system cannot be installed on above ground like equipment, vessel or steel structure to prevent corrosion, because there is no electrolyte available. This cannot be used. Yes, it can be used somewhere for the internal corrosion protection at low temperature services, in the water services. However, for high temperature, the consumption of the electrons or electricity is very high, is not recommended. So now we go, it's like an overview of cathodic protection and its working principles. So we cover two basically sections, and then we will have like when we say before case studies, we will have a break and we'll have a question answer session. So we have to cover like overview of cathodic protection and its working principle, then comparison between galvanic and impressed current CP systems, and give to where's my secretary, not to attend any call. Okay. How do we control corrosion? CP system design, installation and maintenance considerations. Then there would be case studies on the sacrificial and impressed current CP system. Then common pitfall and troubleshooting in the CP system and other compliance with the industry standard. And CPMS software would be the last, just for your information, so as you can stay connected. Here, overview of the cathodic protection and its working principle. We understand already, like we got anode and we got a structure or a pipe to be protected. So here basically there is a electrolyte in between. It could be a sacrificial galvanic anode. Sacrificial mean this anode, and here is impressed current system. Impressed current where electricity is directly connected by converting AC to DC. There are TR units which provide the required flow of current, so as the outflow of the electrons from the oxidation process of steel could be compensated. Sacrificial galvanic CP system relies on the use of sacrificial anode made of a material that is less noble compared to structure to be protected. The impressed current CP system use external DC source like transformer rectifier, solar DC batteries to produce required amount of electrons, and anode material that is typically non-consumable to apply cathodic protection. So here normally there are two methods that can be used to provide cathodic protection, like galvanic one basically for the smaller structures, and ICCP like impressed current CP system is for the big system. Just like here small light coming, so you need a small equipment which should be protected by CP. We provide galvanic type anodes, and if it's a big like a stadium to be lighted, we need more electricity. So here we need to provide supply of the electricity. Is a conceptually showing that what the difference between galvanic and ICCP. Objective of both galvanic and ICCP is same, to protect the main structure which is subject of like a protection, and it should be supported with a proper anode so as its corrosion could be prevented or minimized. Here, like as we said earlier, ACME concept has to be remembered again, like we need to have anode, magnesium or aluminum or zinc, then cathodic metal structure which we need to protect, then we need to also have electrolyte. So, and then there's a metallic wire as well to connect the flow of electron from one item to other. A CP junction box is added in the circuit to monitor the current flow from anode to structure and to assess whether anode is functional or not. Remember, like ACME, anode, magnesium, aluminum, zinc again, cathodic metal structure to be protected, underground piping. Then M, metallic connection through the electrical cables, electrolyte. The anode and cathode should be buried in electrically conductive, I would say, soil and water. CP transformer rectifier or solar system is provided to energize the anode. A junction box is added in the circuit to monitor the current flow from the anode to structure and assess whether the anode is functional or not. Here, for example, this is the junction box. These are the anodes, right? And this power, and here this subject is being protected. So current basically goes from this route. Okay. Now, cathodic protection is achieved when the potential of all cathode sites reach the open circuit potential of the most active anode site. Corrosion on the structure is eliminated. Here, for example, if you see here minus 65 volt and minus 050 volt. So here corrosion would be taking place. Here other side, if anode potential and cathode potential is equal, then corrosion can be prevented. Moreover, cathodic protection is a technique to reduce the corrosion of a metal surface by making that surface the cathode of an electrochemical cell. Next, comparison between galvanic and impressed current system. You have some idea, but as I gave example earlier. So if we say like advantage of sacrificial anode or galvanic, low susceptibility to damage by outside influence, low maintenance cost throughout design life, low cost for segmented electrically isolated structures, then self-contained, no outside source of energy required, negligible interference with the other structures. Whereas limitation, the limited driving force, potential difference is low, like it has a finite life, it can be consumed within certain period of time, subject to seasonal variation affecting operations. Then in acidic environment, the acid directly attack on the anode material and life and efficiency are extremely low. Chemistry of the electrolyte, soil, and the temperature may have an undesirable effect on the basically galvanic anode. Here, if we see the impressed current, like advantages wise, high equipment and installation cost, high maintenance cost, then possible interference problem with the foreign structures, then frequent monitoring. Basically higher, not advantage, I would say disadvantage, but this is the higher equipment and installation cost. It cannot be advantage of impressed current. To me, it has like a advantage as well as this was mixed together. Then here graded, the limitation of this should be reversed. I think there is some error in my slide here. This is a limitation and this is the advantage. Greater driving voltage, high current output, adjustable current output, constant current. These all are the basically benefits of the impressed current, and these are the basically limitations. High equipment and installation cost, high maintenance cost, possible interference problem with foreign structures, and frequent monitoring is required in the ICCP type of cathodic protection. Now, application of CP for facilities and processes. For example, here where we can use. So industry point of view, whether offshore, like a process storage, distribution, like in my experience, CP can be used across the spectrum of the industry, whether upstream, downstream, petrochemical, refining, cement industry. However, their objective of utilization of CP is mainly for the under like soil structures or underwater structures, or limited use is there for the inside of the equipment corrosion protection. So it can be used in all areas. Like second slide coming automatically when I'm clicking one, second slide coming automated. Sorry to stop there. Okay. Application of CP for facilities and like this. Some timer is on, right? Again, gone again. Next, change again. It's changing itself to going to second slide. Okay, right. So application of CP for facility process, like the kind of like assets are covered here, like what is covered under upstream, midstream, and downstream. So in upstream also there are pipelines and subsea structures if the is offshore, and midstream could be a petrochemical plant, refineries, but the equipments are there which can be used. Similarly, downstream also the equipment nature is same in all the spectrum of the industry, whether upstream, downstream, or midstream, or we can say onshore, offshore. But utilization of the CP is effective in all areas. But limited use for underground pipelines. Nowadays, industry is not burying piping system because it's difficult to maintain the integrity of the underground piping system, small one. But pipelines are still underground, and cross-country pipelines are mostly underground, and they are protected by the CP system. And similarly, offshore pipelines which are coming under the sea or subsea structures, those are also required to be protected by the CP system. So similarly, some areas inside the equipment, some corrosion protection whether galvanic anodes or the ICCP system is installed also in the industry. Now, application point of view, as we explained earlier also, marine and seawater application like outfalls, sheets, steel piling, jetties, ships, submarine pipelines, and production platform, those are protected by CP. Similarly, buried structure and pipeline, plant piping, foundation and footings, tanks and storage tanks, buried tanks like externals, steel and cast iron pipelines, reinforced concretes, then vessel and tank internals also sometimes protected with the CP system, as I said, whether galvanic as well as the impressed ground storage tanks, then production vessels, heat exchangers. Its utilization. Now, here, how do we control corrosion? I touched this subject earlier also when I started my presentation. But in general, proper selection of material of construction as per process requirement for the equipment, pipelines, piping, and other structures, internal cladding or metallic lining to prevent the internal corrosion, coating application, internal, external. Then corrosion inhibitors are being injected to control the corrosion. Then this cathodic protection comes. Internal, external, both can be used. Type of CP, internally, internal, typically galvanic. It could be generally, typically, but it can be also ICCP in the bigger tanks. Then external, both galvanic and impressed currents are being used. Here, the direction of current flow is important in the corrosion process. The electrons flows from the anode to cathode. It is a repetition coming. But the people who are new, so as we can remember the things, under cathodic protection, electron flows from anode to cathode, and cathode is protected from the losing of those electrons, which normally iron, Fe, while combining with oxygen by making Fe2O3, lose those electrons. Those are compensated by the anode. Notice the current flow through both the electrolyte and metal path. Electron flow only through the metal path. We discussed this subject earlier also. Where the current lands, there is no corrosion. Where it is discharged, there is a corrosion. Mean anode is like a depleting, and cathode does not deplete or does not corrode. Here, other part. Now, like when a pipeline is or equipment, when we're talking about external corrosion, so there is a very high rate of electron loss because electrolyte is there, and there could be a natural flow for the oxidation. So to minimize outflow of electrons, like when pipeline itself start working as a anode, to prevent, it should not act like a anode, and we should be able to put the barrier so as potential of outflow of electron could be minimized. So coating is one of the major protection to as a barrier to minimize the outflow of the electron. The coating provide a physical barrier between the metal and the electrolyte, prevent the amount of water and oxygen or hydrogen ion that diffuse into the metal surface. The coating also places an electrical resistance in the current circuit, prevent galvanic corrosion cells. A holiday or breakage, or there could be any imperfection, is a discontinuity in coating film, a wide crack, thin spot, foreign inclusion, or any contamination which will lower the dielectric strength of the coating. A pinhole is a small pore like flaws which, when extending entirely through the film, represent a discontinuity. See here, the metal dissolution process in aqueous environment produces metal ions, electrons, and corrosion products. However, some metals are protected by the corrosion product films. Now, type of coating systems, we should know that there's like a primer coat, intermediate coat, and top coat. These are three coats. If you see here, like a primer is a substrate and basically a steel pipe, and then intermediate coat and top coat. So these are made three coat to minimize the imperfection in the coating system, so as this barrier could act effectively. There are various type of coating systems, like here, for example, asphalt or bitumen coating is there, which operate up to 60 degrees Celsius, and its life is 10 to 15 years. Compatibility with CP system, good in early life, very poor in the later life. This is the case. These limitations are there. Inspection for corrosion is best carried out by intelligent. I'm not in the favor of intelligent pigging personally. Then maximum operating, next is the fusion bonded epoxy coating. Maximum operating temperature could be less than 90 degrees Celsius. Compatibility with CP system excellent. Expected design life is 25 years. Fusion bonded epoxy. Industry experience, this thin film coating does not exhibit very good mechanical properties. Limitation, application tolerance small. Substrate preparation, cleanliness, and temperature critical for successful applications. Here, like a fusion bonded epoxy coating, this is the like a pipe, and this is the epoxy bonded. Now, this is a more nowadays a more popular kind of three-layer polyethylene or polypropylene coating, which normally work effectively up to 75 degrees Celsius. Expected design life 40 years. Thick film coating is ideal for harsh conditions, provide good anti-corrosion protection and mechanical protection as well. Next, the application tolerance small, the substrate preparation, cleanliness, and temperature critical for the successful application, require a well-designed and managed coating factory line, require close attention at field joints. Like here, three-layer, this is steel, then 1, 2, and 3. So these are more common like type of coating which is being used externally for the pipelines nowadays. Then heat shrinkable sleeves for the grit weld joint. This is also important for the field joints, as you can see this, like adhesive directive to line coating, then main line coating, then hybrid adhesive technology, and pre-attached closure system, and force cured epoxy on the steel. So this is also one of part of the three-layer polyethylene coating, because field joints has to be made by the heat shrinkable sleeves for the grit weld joints. Maximum operating temperature up to 80 degrees Celsius. Expected design life 40 years. Cross-linked and stretched polypropylene backing coated with a polypropylene adhesive. Limitation, application tolerance small. Substrate preparation, cleanliness, and temperature critical for successful application. Require close attention at the field joints. Properties point of view, if we see that here, effective electrical insulator, effective moisture barrier, sustainable addition to the pipe service, ability to resist development of holidays with time, ability to withstand normal handling, storage, and installation, ability to maintain constant electrical insulation with time, resistance to disbonding, ease of repair. If you see that this is the coating and electrolyte is above available, and this is the metal of the pipeline. Non-toxic interaction with the environment is also one of the criteria. Now, there are corrosion inhibitors, if you know that, like from the corrosion background, there are various corrosion inhibitors which are used for internal corrosion, whether like methanol, glycol, like based or methanol injection for the dehydrate formation, prevention of dehydrate formation, and then also another inhibitor to minimize CO2 or H2S based corrosion. So these like corrosion inhibitors are three types. One which form the precipitate that visibly coat and protect metal surfaces. The corrosion inhibitors are mostly used for the internal part, not for the external part, which are injected with a process fluid or with a gas. So CIE form, corrosion inhibition form, like a precipitate that visibly coat and protect metal surface. Then there are combined with corrosion product film to protect the metal surface, silicate and like molybdenate in the cooling system. Then adsorb on metal surfaces to form monomolecular protective layer, organic molecules in oil and gas system. So here, like perfect coating mean no holiday. Other one, if you say coating holiday, if the break is there, then coating and cathodic protection together, then like here, perfect coating, you don't need CP system. However, if there are holidays, pinholes in the coating system, then we need to have CP system. So the CP system and the coating system works hands in hands. Cathodic protection current require to protect the anode area. Coating breakdown is substantially reduced. Then primary protection and secondary protections are also there. Like when we say primary protection is by coating and secondary protection is by the CP system. Primary protection, coating and painting, and secondary protection by the anode. Secondary protection by providing sufficient electron into the metal using external DC electron source, galvanic, anode, TR, solar, whatever system is, the process of electron discharge will be reversed. This method is known as cathodic protection, secondary. So, as a definition point of view, creating a corrosion cell, placing two dissimilar metals, right? Like how we normally make this combination, like cathodic protection, like a cathodic copper, anode steel, or there could be, for example, copper and steel, and there could be copper and steel. Various potential differences are there. We can say mechanical, electrical connections, remove connections, then what will be the scenario? Change copper to steel, what would be the scenario? Add aluminum to zinc, what would be the scenario? So there are like various kind of acme combinations which could be tried while designing the CP system. So you have to keeping time in mind, so I have to go a little faster. So here, brief cap, for example, like let's try to understand here. The best corrosion control package is coated and cathodic protection combined. Like this is basically the take up to now. Coating provide first layer of defense against corrosion. Cathodic protection provides second layer of protection, right? Cathodic protection can be achieved by introducing a less noble material having more electronegative potential than the most negative potential observed on the metal to be protected. So before we go to the CP system design, installation, and maintenance, like before case, I think we can cover that also a little bit, and then we go to the basically break for the question answer. So here, when we have a CP system design, installation, and maintenance consideration, so here we take one example, like a design life of the asset, pipeline, carbon steel service to be protected, type coating, coal tar, or P epoxy. Then coating breakdown factor according to the coating we need to understand. Then exposed metal surface area at coating defects. Then soil resistivity, soil analysis, sulfide, carbonates, chlorides, and pH. Important. Degree of corrosiveness we have to see externally. Electrical isolation, foreign structures like earthing, pipeline crossings we need to consider. Then protection criteria, minimum -850 millivolt and 100 millivolt shift. Then current density, what we need to cover, milliampere per square meter. So here, if we see that as a result, we will preparing this sheet and the calculations. So we will be covering these parts in next stage. This process is essentially iterative in nature because we need to meet multiple conditions at the same time to optimize the cost. This is not so simple, but there are simple calculations and we can make it little bit difficult as well. So before we go to next stage, we take the questions, and for question answers, my colleague Mr. Abdullah from Pakistan, he would also be helping us. Yes, Mr. Shahid?
Yeah, my voice is audible.
Yes, yes.
So my question is how frequently we can monitor the CP system specifically for underground piping.
See, normally if I may try to answer this, you got the test posts according on the route of the pipeline, and then there are TR points. So various companies are having various like frequencies. It varies like for the test point from 1 month to like a 6 month basis, and the TR testing is normally yearly basis. but it can be established based on your own experience and company strategy. Like if you have developed your inspection and maintenance program for the CP assets, then it can be basically fixed based on the mean time between failures. Like if you have seen problems with your CP system, then your frequency has to be increased. Otherwise, it can be extended for a longer period. Okay, sir.
So there is no.
No, it's okay. No. See, as such, there is no thumb rule to follow it. It is basically adjusted as per the company policies. As I said, a monthly monitoring of the test post to 6 monthly monitoring, and the TROIs, you have to see that if something is going wrong. Right.
Got it.
Okay. The question is how the surface area of exposed metal can affect CP. Will a node be sacrificed more quickly? Yes. Like normally, when pipelines are protected by CP system, it is understood that the pipeline would be protected by coating system, and the coating failure rate would not be more than 1% maximum per year, or maybe lesser. And if it would be having more failure of the coating system, then the current requirement will increase, and the anode would be like like if you say sacrificial anodes, it would be consumed more fast, and that is a normal consequence. Mr. Abdullah, if you would like to answer this question, if you can see the screen. Question from Zain Ali Abbas.
Yeah, basically, the more surface area will be exposed, the more current requirement will be needed, and the more current will be needed, the more anode will be sacrificed. So it's a linearly proportional. Okay, higher the current, higher will be the anode consumption. So that's the reason we are having a different type of the coating system. So, and we maintain the coating system to have a less surface area exposed to the environment. Lesser the surface area exposed, lesser will be the anode consumption. Hope the answer is there.
Okay, good. Next question, please, quickly, because we need to complete the session also before 4.
Okay, Mr. Shiraz Ali, we are unmuted. Please ask your question. The question was, pegging can monitor internation corrosion.
Basically, internal corrosion, basically. See, intelligent pigging can help to find both internal and external corrosion or metal losses. But it depends like what kind of technique is being used, whether MFL technique or UT technique, and how accurate is the pigging tool from the basically inspection company. Next question, please.
Mr. Kashif Afzal, your question was, does ICCP
No,
anodes...
first give him chance. First give him chance
Yes,
to ask.
you're unmuted. Can you please speak?
Hello, sir. Good afternoon.
Good afternoon.
Sir, I would like to ask that you explained that in galvanic CP, the anode itself sacrifices and gives electrons to protect the other part. So, in case of ICCP, the current is basically supplied from the transformer. So, the anodes, does they have a limited life, or they also, kind of consumed over the time?
In sacrificial anode, the anodes are self-generating current. So all the
Yes.
current, all the electron which are needed to protect the cathode is supplied by the anodes. Okay, whereas in the ICCP system, we use the non-inert type of the material which is not supplying current by itself. It is only passing the current received from the transformer rectifier unit or the solar system and pass on to the cathode. So here they are working as a postman, but still it does corrode, but the time is almost 100 times less than the sacrificial anode.
Thank you, sir.
Some consumption would be there. Okay, next question, please. Mr. Arisudhan.
Mr. Arisudan, you're unmuted. Please.
Yeah, good afternoon, ma'am. Good afternoon, sir. My question is regarding PSP off readings of the sacrificial anode system. Means, is there any guidelines for doing that? Because we'll have our connection at different spots. Means we'll have a connection at multiple spots in our sacrificial system. Is there any way we can check the PSP off, and what is the necessity of it?
Yes, in the sacrificial anode system, although we cannot interrupt the anodes to go for on and off, as we have the facility in the ICCP system to switch on and off the transformer rectifier unit, but still we can measure the off potential of the sacrificial anode system by doing the coupon. So what we do, we have a polarized coupon, okay, test pose, where we interrupt for a moment, and the same anode can disrupt the supply. So by using the coupon potential, we can measure the off potential for the sacrificial anode system. So here we use the coupon potential that will give you what are the IR factor. So the same we will apply onto our pipelines.
Okay, good. Next question, please. Because time is important.
Yes, Engineer Zain Ali, you're unmuted. Please speak.
You can read the question.
What is the voltage of CP system?
I already answered in the chat box. Basically, it depends upon the anode and cathode, the potential difference, because the anode are placed onto the soil and the cathode, so there is a potential difference. So there is in the next slide will also explain the same thing. What are the resistance in between the anode and cathode?
Okay, and Mr. Prakasa Rao.
Yeah, good day, sir. Is CP used only to protect carbon steel only?
No, it can use for the stainless steel and the other thing as well. But generally, carbon steel are the most commonly, because the carbon steel are more in the soil application, and it are used in the seawater. So all our pipeline, our tanks, they are used on that. But we can provide a cathodic protection to stainless steel and other material as well.
So in that case, the anode can change.
Yes.
Okay, thank you, sir.
You can go to
Mr.
question.
Ahmed Wagih, you're unmuted. Can you please ask your question?
You can read the question. Okay. Yes, Mr. Ahmed, please your name and location or organization, if you can tell.
I have answered almost 32 questions in the Q&A session. So meanwhile, I will be answering. I think so, Mr. Ejaz, you can continue because the time is less.
Okay, so we're going to go back to the presentation, and then we'll come back at the end. And if some of the questions are not answered, we'll try to have an interactive question answer. Mr. Abdullah, it's better if we can have an interactive, so we know that what the kind of interest of the people and what kind of questions they are asking face to face, right? It will also make them participant in the session as a vocal, right? Okay. So case study will be covering first as a sacrificial and then ICCP. So you can understand that as a case study, I would be also going through the in glance, and it cannot show all the calculations because calculations are complicated. But in my view, it is not so complicated, but still there are calculations, equation, empirical equation which are being used. So please bear with me, it would be faster. And then we have to also show the our VAIL-Plant CPMS system. So then it will conclude the session. We are trying to complete before or around 4. So here, let's say there is a network of pipelines, and we have taken one pipeline with diameter is 4 inch and length is 300 meters. Example. So here, like what we need to establish if it is a sacrificial type anode. So remember sacrificial type anode where we have to sacrifice our anode. So we need to know what is the basically first what is the current requirement and life, and then accordingly what is the mass requirement of the anode as per those calculations and needs. Then what we use in a normal basic input data. See, okay, let's say something got changed from my previous screen to here because the line is 6 inch, not 4 inch, and length is 300 meter, not the. So it's action for my team because the line was upper, not lower. So the second line we are taking ABC line, not the third line. So okay, we take a note, and the diameter is 6 inch and length is 700 meter. Surface area pi d L. Then surface area allowance earthing A into K factor. Then current density in soil, which is here 20 milliampere per meter square. Increase 25% increase per 10 degree Celsius rise in temperature. This equation has to be done. Then design temperature 40 degrees Celsius. corrected current density at 40 degrees Celsius, which is 25 milliampere per meter square. Then final coating breakdown factor CBD, which is 10% 0.1 of epoxy coating. 300 DFT is the thickness of the coating. Then current requirement is coming as IA is A into CD, and CD, this equation multiplication is there. Soil resistivity coming and playing its role, which is 2000 ohms per centimeter at 1 meter and 1000 ohms per centimeter at 2 meter depth. Then pipeline natural potential, which is minus 0.5 with respect to this cell and 0.95 with respect to other side. Then protective potential of is 0.95 volt with respect to CuSO4. Here, then calculation wise, so coating breakdown factor is being calculated with this equation, F initial, F mean, F final, and equations are there. And then the type of the coating is 3-layer polyethylene, and so these factors are calculated. Then accordingly, the other like a DNVGL formula is also there, another way of calculation. Here, current density milliampere per meter square. So onshore pipeline, buried steel plant piping. So here, fusion bonded epoxy, and then external surface of buried vessel 0.3. Pipeline and storage tank bottom is 10. It is taken from here. So there is a various current densities as per the SACP system. Then current demand calculations are calculated with this formula, which summary is given earlier. Then J is the typical design current densities for bare steel or cast iron pipeline should be in the range of 10 milliampere per meter square to 1 ampere per meter square mainly. Then the selection of the galvanic anodes. So here, what type of anode we'll be using and their environment, what kind of environment we can use, then their efficiency factor, and then the potential reference of electrodes, then capacity in hours. It will go by the, it will help to assume the consumption rate or age. So the best one, if you can see here, is zinc one, and so 90% coming as a efficiency, and this is a greatest like AGL potential, and then capacity is coming 740 to 760. Like no, bigger one is coming aluminum one, 800 to 2750, and the consumption rate is coming 3.9 to 4.8. So this way we have to select what type of anode we want to use. Then here, selection of galvanic anode, for example, the weight wise, if their weight and size, diameter, length, weight, then OC potential, electrolyte capacity, consumption rate, and utilization factors coming in the picture. Then anode quantity based on anode weight, like how many anodes would be required. First the weight and the number of anodes coming in the like 3.6 is to 4 numbers. So in this way we can calculate the number of anodes required and the weight of each anode as well. Here CP equivalent like a electrical circuit where we have to see R pipe to ground, resistance per pipe to ground, resistance from anode to ground, resistance from inside pipe, and these all are combined to see what would be the combined effect on the size of the basically sacrificial anode. Here anode to earth resistance, like here if it is a vertical one, so then we have like a anode inside, then we have the backfill soil, and we got also the upper final part which is like a membrane, or we got coffin. Like a galvanic anode is here, pre-packed like a chemical fill is there, then lead wire to junction box which is connected with the basically potential cathode. So from anode pre-packed in chemical backfill, the total anode to earth resistance include the resistance from the anode to the outer edge of the backfill package, 50 ohms per centimeter. The resistance between the backfill package and the soil may vary from 500 to 10,000 ohms per centimeter. The contribution of the anode to backfill resistance is insignificant compared to backfill to soil resistance, typically much greater than the resistance of the backfill. Here anode to earth like a resistance, horizontal single anode, if is there, this is the formula and we can calculate it. Second one, if we have anode to earth resistance single vertical, this is the formula and we can calculate it. I'm just showing you because time is not there to go through the all detail. It takes a lot of time to go through this process. Then Anode to earth resistance multiple vertical. If it is coming, the equation is there. Then anode to earth resistance multiple, same calculation going next. Then here anode to earth resistance multiple vertical is completing the calculation, basically this part. Then anode current output, like I anode is equal to delta V over RA, and this way if one available is greater than required, then it would be considered acceptable. Then next is anode design life validation of 5 number of magnesium anodes, each weighing 27.7 kg. So this is the formal equation and calculations are made. Then if you see that sacrificial cathodic protection here, when system is off, mean you can see that ions from the Fe are going into electrolyte, and the cathode, like the anode, is unable to protect and it's losing its ion also into the same electrolyte. But when the circuit is closed and it's working, then the cathode is being, our pipeline subject is being protected, and the ions are being like our electrons are being compensated by the magnesium anode, and it's sacrificing to protect this pipeline. So this is the difference between the unprotected system and the protected system. Now we go next, like the same way, short presentation of impressed current calculations. Like here we have a pipeline which is 24-inch diameter, 100 kilometer. Design life is the length. Then design life is 30 years. Coating type 3-layer polyethylene. Soil environment is moderate, which is like a resistance 4000. Interference and crossings is there, HVAC, foreign pipeline, plant earthing, and city road crossings. Protection criteria, polarized potential 850 millivolt and 100 millivolt polarization. Then these are the NACE standards which are applicable standards. NACE like 0169, then ISO 15589 part 1, 2003 it is, and BS ISO 15589-2015 and other NACE standards. BSEN 12954 and BSEN 14505. So the total structure surface area is in contact with the soil or other electrolyte buried submerged pipeline. Then surface area not intended to be protected, earthing above ground pipes, overhead crossings. Then pipeline battery limit, location of isolation joint at the both end of the pipeline. Then this is a formula, normally pi dl, and tank bottom plate if you have to use pi r square. So surface area calculation as per the formula, and then here is the initial, mean, and final coating breakdown factors we calculated, and this would be the like factors what we'll be taking from the standard. Here like current demand based on the coating breakdown. For new pipeline, the total current demand would be calculated this way. Then accordingly total I is calculated based on the factors which are applicable. Here like this is 0.4 is a basically factor as per ISO 15589-12003. Here like onshore pipeline, 24-inch dia, 100 kilometer, 3 PLE coated pipeline for 30 years design life. Mr. Abdullah, if you would like to add some more, because we are going through the like last part of the presentation on the ICCP calculations. If you would like to add more details, it would be beneficial.
Basically, for any structure, for any pipelines, you need to know the 3 things. One is the surface area, which is exposed to the ground, exposed to the seawater, exposed to the soil. So example over here, we having a 24-inch dia, 100 kilometer, which has a 3-layer polyethylene coating pipelines. Okay, and this pipeline is designed to protect for 30 years life. So if we go to the first slide, one previous slide. Yeah, here it will say what is the current required to protect these pipelines. So that have the 3 parameters. One is the surface area, which will come with the pi dl, the surface area, but that is a bare metal surface area. On top of that, we have a coating. It means your surface area is not exposed, the whole surface area. So we maybe what are the coating breakdown factor, Mr. Ejaz already explained. But generally, you can say it varies from 1% to the 10% over the 30-year life. So it means you need to protect 90% of your surface area. Then what is the next factor? This 10% surface area, how much current density you need. So here is the different standard that giving us what is the current density, the milliampere per meter square. So 1 meter square, how much is the current is required? Go to the next slide. This is the, if you have asphalt coating pipelines, okay, as per ISO 15589, that required for 30-year life 60 ampere current. If we go with the optimized design, and if we go with the conservative design, it requires a 160 ampere. So it means you need to a transformer rectifier unit of 160 ampere to protect your pipeline, which is the asphalt or bitumen coated. But the same pipeline, if it is a 3-layer polyethylene, that will require only 10 to 40 amperes. So here we will calculate the current requirement. Next slide. So this is the current demand calculation. Another you can say the method to calculate surface area is the bare metal surface area. For a bare metal surface area, if it is exposed in the resistivity, which varies from 50 to 500, it is a coastal area. So your bare surface area that requires 20 milliamp per square meter and maximum 40 milliamp per square meter. So this is a different way to calculate the current requirement of the pipelines. And same is applied with the sacrificial and the impressed current. So here we are calculating for this 100-kilometer pipeline, what is the current required. If we use according to the resistivity calculations. So this comes 80 amperes. Okay, 40 plus 39 point by using these ISO formulas. So then what is the 80 ampere current requirement? So we can do the how many are the length we can protect. Okay, so 1.14 ampere is required per kilometer to protect these pipelines. Next. So another method, what the method already explained is by the desk engineering, by the paper calculations. So we use with the soil resistivity, we use with the coating breakdown, we measure a lot of things. Another is the direct method. Okay, you have one pipelines, okay, and you know what before application of the cathodic protection system, you measure the natural potential. Example, we have measured this potential and it varies from 0.5 volt or 500 millivolt to 700 millivolt. It may be in some location, it's up to 100 kilometer pipeline. You can see and thousands of reading, and that it is recorded. We call it a native potential survey, natural potential survey. So this natural potential survey, so we will calculate, and then we applying slowly the current, like starting with the 2 ampere current, and then we see how it is a change at that location. The moment all the anode and cathode potential are minimized, okay, so then it means that current is required. Or we have a NACE applied 850 millivolt. If we are measuring in every location, after applying the temporary CP system, it is 850 millivolt, and then we can measure how much is current is required. So example, one contractor already installed a pipelines, and we have measured the potential, which is 850 less than 850 millivolt. So he keep on applying the current until he achieve minimum 850 millivolt wherever we measures. So that we call the current drain test. Next. So then there are the different anode, okay, the selection of the anode, as we do the same in the sacrificial anode, magnesium, aluminums, or the zinc. Here we use the impressed current anode system. This is the mixed metal oxide, which is most commonly used. It also gives the anode to electrolyte resistance, as we measure into the sacrificial anode in the case study for sacrificial. So as I said, in the impressed current CP system, the most is the anode to electrolyte resistance. There are different formulas for the different type of the configuration of the anodes, whether it's the deep well anode, whether it's the horizontal anode, or it's a discrete anode. So different type of the system we use and different type of the formulas are applied. Again, here this slide represents what type of the anode material which are preferably used. We can also use the scrap steel, the same old pipe which are in your store. You can also use as an anode material, but this will be diminished. This will be expired very soon, because for 1 ampere current, the 10 kilogram of the pipe will be consumed. It means you need to replace that anode bed very often and very frequently. So then there is a graphite, high silicon chromiums, mixed metal oxide. Nowadays, the mixed metal oxide is the most commonly used all over the world, which compared to the pipeline or the high silicon, which have been used in 1980s and then 1990s, this high silicon chromium, this is only a less than a milligrams. Okay, you can say over 0.005 milligram per ampere per year. It means, as I said in the last question, it's just a postman which are taking a current and passing on to the cathode. There are other as well, platinized niobiums, which is even less than that. So how we can measure whether your anode can work in this environment, and what would be your transformer rectifier unit capacity, what potential you need, what voltage you need, what current you need. So then we should have a soil resistivity. The soil resistivity that gives you the indication how the soil is corrosive, like in the desert. Sand is very high resistive environment and less corrosive, whereas in the near to coastal area, it is the very less resistivity and highly conductive and highly corrosive. So resistivity and corrosivity are inversely proportional to each other. Higher the resistivity, like in the sand dune in the desert, lower is the resistivity. Lower is the resistivity, it means you need a less current to fight. Then next, apart from the resistivity, you need to know the resistivity, pH, moisture, chlorides, sulfides, other bacteria. So if we combine all these things, so the area which are having a less than 1000 ohm centimeter with the pH 4.5 or less than 4.5, and the chloride contents greater than 1000 ppm and the sulfide greater than 5000 ppm, that soil is very aggressive, very corrosive. It is near to the seawater or to the coastal environment or the marshy area or to the subka soil. Whereas the soil which are in the between 1000 to 10,000 and the relatively the pH higher and the chloride lesser than, so then it will be a high, medium and the low. So we can categorize our soil work. For the CP system to work, we need a low resistive so that the current can flow, but for the pipeline you need a high resistance. So then this is a different type of the CP system design, like we design any our house or any villa or anything, we have a different lighting system. Okay, so obviously for the small lights, it's got a small anode in the different location. We call it a discrete anode system. Like over here, if we have a pipeline with the 5-water pipeline with the main pipeline or the branches pipeline, so rather than having one anode, we can divide our anode on different location. We call it again in the discrete anode system, like we have shown in the previous slide, like in the villa. So this discrete anode system means this anode will cover one area, another area, another area. This is more, you can say, reliable area. But obviously, the anode installation work or the cost will increase. Here, this is then one anode, one deep well, okay, which comprising 10 to 20 anodes on the vertically installed over here. And that one deep well anode can even protect a long distance pipeline up to 40 kilometers, or it can protect tanks of like a 50 meter up to 4 to 5 in the for the one, or one larger tank of 100 meter, one deep well ground bed. So it depends while what type of the anode bed we will be economical and will be more accurate. Another simple way, okay, if your soil is already marched, you can say the like in Pakistan, we have in our company, so in Northern Gas, we are having a long distance pipeline, and that distance pipeline passes through the cultivated land. And the cultivated land, we already have a moisture environment, so we can have an anodes next to the pipelines. So this is a deep well, can be a one anode up to a 10 to 20 anodes vertically placed. And then here we can define, and all obviously we are having a series and parallel configuration. So the way we will design the configuration of the anode bed system. Over here, you can see the one pipeline, long distance pipeline. We are having Saudi Aramco is generally use this type of the arrangement by you having a 5 to 10 anodes vertically at one location, and every 20 kilometer, every 30 kilometer, you can have an anode bed that can protect a certain area of the pipelines. Again, same, different configuration, different formulas. This is the same example. If you can use the scrap pipe as well. If your example, you are unable to, your anode bed failed unaccidentally, and then procurement of the anode will take time. So you can use the scrap anode as your temporary anode system for 1 year or 2 years till you get the material and you can install the anode like a graphite, mixed metal oxide, or high silicon chromium. This is a sum up, okay, example over here. So the designer generally check all type of the anode beds, like if we can go to the surface ground bed horizontally, obviously the resistivity is high. The more you go deeper, so the resistivity will come because the more moisture will come. So if you are installing the deep well anode bed with the 10 anode, or compared to the horizontal anode bed with the 10 anode, on the right side, you can see what is the resistance you will get. The resistance of the ground will be 2 ohms if we go with the horizontal, while if you go with the deep well, it will be 0.10 ohm. Lesser the resistance, is more beneficial for the ground bed, and it will go more faster. So from here, we can see which one is the more economical. Obviously, for deep well, you need a deep well boring, drilling to go deeper. So then this is the cost element we study, which type of the requirement we can go. And here you can go for the one area to other area. In one location, we have a CP station. In some location, your one CP station, one ground bed system can protect 30 kilometer on either side. It means it can cover up to 50 to 60 kilometer. But you have to be careful by doing the attenuation calculation. Okay, this is the two method. One, we can measure when the pipeline, when the anode system is installed by doing the pipe to soil potential measurement. But for other, because before design, you can do this attenuation calculation as well by using this formula. This is another method which is very popular, okay, because we are having in the plant system, if we have a pipelines, so the anode is laid on the same trench, okay, and this is a new cable anode system. So, and that go along the pipeline. It is all the length of the pipeline having an anode. So there is no need for attenuation calculation. There is no need to check the design. Whatever is the length of the pipeline, if you install the anode without even calculation, it will work. This is a recent development. And this type of the anode, like you can see, this is a pipeline and the anodes are being laid on the same trench. It means you are having the entire your pipeline having the anode system like a light. So there are the different formulas to calculate whether this length will be sufficient of the anode, this anode will be sufficient current, the attenuation calculation. It's all for the before application of the design. There are some certain formulas.
So if I go back to pitfall, I can take over, Abdullah. Like here, the disbonded coating, like is a one area where we estimate 1%, it goes to 10%, then CP system will not be effective. So this is the area we need to have a right estimate, like what could be the problem with the coating system, or how much bare system of steel would be required to be protected by the coating, by the CP. So none of the surveys work if the pipeline coating is disbonded, which exhibit no electrical continuous pathways to the soil, thus shielding will not be available. This is one of the major drawback for the CP system. Secondly, like there could be a measurement errors. For example, we have a voltmeter, we have reference cell. Here, if any of these areas may give wrong report, then system may not be protected. The calibration and the testing of the system is very important to make sure CP system is working effectively. The aspect, right? Yeah. The whole system. Anything which is not giving accurate number, it can lead to a different problem. Then measurement error, same way as we said earlier, the calibration of the all components is required to be properly done and properly checked. Here protection criteria also, like whether minus 850 millivolt or minus 950 millivolt for the where the protection potential for steel is in anaerobic soil environment, then overall protection limit for the carbon steel minus 1150 for copper sulfate or the AgCl environment or zinc environment. So this is important to see if we are within the acceptable range of the protection or the potential difference. Here, like what we need, like first we need to have attain protective coating, cathodic protection. Attaining a pipeline integrity is much easier than trying to maintain it. Attaining variable are straightforward, but we need to maintain operations, test and monitor. Then there are 3 R's, for example, repair, refurbish and replace. These things are also important to have effective results from the CP system. Then like there could be a simple CP survey. We did not give the timing here, like only TRU monitoring, then DRU monitoring and PSV surveys, and their third level could be TRU monitoring, PSV surveys, DCVG surveys, which give 70% confidence. Then level 4, which is the best one, TRU monitoring, PSV surveys, DCVG surveys and SIP surveys, which can give you 100% assurance. So the message is like surveys are important to have confidence in the CP system. So like this we covered earlier, so I will not go through this again. This is another area, we leave it. Now, compliance with industry standard. Here we referred this standard in the ICP side as well, ICCP. So here these standards works in combination along with ISO, NACE and ISO, then ASTM and like a DNV-GL or nowadays DNV standards are also useful for the offshore side. So these standards give assurance for the users and the operators. Then last part of our module, like Velosi has developed like a complete integrity management solution, which consists of various modules like pipeline, PIMS, pressurized equipment management system, pipeline, integrity management system for both onshore, offshore, structural integrity management system, lifting equipment management system, electrical instrumentation and rotary equipment management system. Here is a civil integrity management system. Then CPMS is a cathodic protection management system, PSVMS, hull integrity management system for the ship, well integrity management system, and CMS is a computerized maintenance management system. So we have a calculation engine, we have a analytics, and then reports and dashboard. So we have also 3D intelligent drawing, SAP integration or the overall CMS, then historical and documentation, then condition monitoring, laboratory information. So it is a risk-based approach. Basically, we apply whether it's a risk-based inspection or reliability-centered maintenance, or still all 3 approaches are used to optimize inspection and maintenance routines. So here for the what we do under this particular system is we have to develop asset register in accordance with ISO 14224, then feature to carry out FMEC analysis for the CP system, identification of functional and failure modes, then identification of failure causes and maintainable items, development of reliability model and reliability analysis and reporting, identification of FTP-based bad actors, anomalies and risk-based trends. Then probability of failure and consequence of failure calculation for individual equipment or tag, then development of inspection and maintenance strategy, development of PMR and job plan for the CP system, then integrity and risk dashboard, standards and custom query reports are also part of the system. Here we got certain various this is a modular approach. It is easy to use and it is also well tested and being used in the industry by various clients and major players in the oil and gas sector. Here in cathodic protection, what we try to cover is the ground beds, then negative junction boxes, anode junction boxes, anodes, TR units, coupons, test points, and solar panels. So all particular units we cover under our CPMS system. So here CPMS dashboard predict overall status of all the cathodic protection systems, 7-level hierarchy tree for CP system dashboard, dashboard management system, CP system design and construction database, schedule routines, field data testing and monitoring, then graphical display of quick view and trend analysis, failure mode effect and criticality analysis, plant maintenance routines, custom query, then standard reporting, reference documents, then continuous improvement to customize client requirements. So this is the dashboard where we can see like the risk point of view, and as also the inspection activities if those are done, then transformer rectifier, anodes and their activities as a result. So here like we try to see the one like a TR unit, its components. If you see that like ADJB, anodes, coupons, NDB, NJB, PDB, PRE, test point, TR unit and their relevant data is also given like TR engineering data, PDB engineering data. So we have made a specific engineering data for each system. Then design parameters of the system, equipment and material data sheets, like installation date, like renovation date, installation scheme, as-built layout, monitoring facilities, and commissioning status. Then under FMECA, we try to identify like all the failure modes, like for one particular item, overheating, then spurious operation, structural deficiency. The next like inspection point of view, the data is there, we can store the data. Then identification of the basically some problem is there. So here we can see liability wise and bad actors based on the data or the risk position of each component. Probability like a failure assessment on the liability database we do. Then risk matrix is there to show the risk position of that particular component. Then PRs like PMRs or the plant inspection routines or equipment inspection routines or maintenance routines, what we need to develop based on the failure modes and the like MTBF data with the frequency and activities. Under those, we also prepare the basically job plan and then taking into account the failure history of that particular equipment, how many times the equipment failed in past. So either testing and monitoring, like these are the PMRs, like what we need to do over the period is a plan, what should be executed. So the more details. Then there are various routines are there, like a Anode inspection report generated. And similarly, we have a reference document which we can attach as a single line diagram or the electrical system layout. So this concludes our discussion. We are around 4:05, but still we can take few questions before we close the day. Mr. Abdullah would be again helping me to answer the questions.
Mr. Ahmed's question was, can you provide references for projects where a CP solution was a feasible solution in terms of acidic environment that consumes the cathode? What would be a preventive action in this situation?
Can you please reference for projects where CP solution was feasible solution in terms of acidic environment that consumes the cathode? What would be a preventive action in this situation?
Yeah, in the acidic solutions, generally the cladding is the best solution, so that the material study, the material selection is the most. Because for the if you're having an internal corrosion or the acidic environments, okay, so definitely there will be a coating and that will not work over there.
Okay.
But if you are having the pipeline in the acidic environment, yes, it can still work, but you need to have a higher amount of the current requirement in the acidic environment because the pH is low in the acidic environments, the resistivity is low, so you need to have a more robust CP system.
Mr. Qasim's question was, for cross-country pipelines, will CP criteria will be dependent on pipeline length or environmental aspects are the main criteria?
I repeat the question. The question is for cross-country pipelines, will CP criteria will be dependent on pipeline length or environment aspects are the main criteria? I think both, but you can give more details, Abdullah.
No need. The criteria will remain the same. Only the design factor will change. The criteria is to attain the same performance potential, but obviously to attain that, Okay, in the low resistive environment, you need more current. Protection criteria will remain the same.
Okay. So next question, Mr. Kamran Sagir, can you please unmute? When we unmute, can you ask the question? Mr. Kamran Sagir, you're unmute, please ask the question. The question is selection of material for pipeline for water treatment plant can increase the efficiency effectiveness to avoid corrosion. There is a question, Mr. Kamran, from your side.
Yes, sir.
See
It's from
here,
my side.
mostly CP is focusing on the external corrosion, right? And
Right, sir.
if the line would be underground. Now, if you're talking about internal corrosion, the installation of anodes internally would be a difficult task, depending on the diameter of the pipeline. However, it can be used as an option.
Yeah, generally for the water line, the good coating, okay, are used, okay, with epoxy coating and some robust coating system, GRFE, for the pipeline. But if we are having only carbon steel and the originally pipeline is some bad coating, so then you can supplement with the internal CP system using the mixed platinized niobium anodes. But this is generally not used for the internal piping, which is very, very difficult and very challenging task. All the material that copper nickel type material is used for the water pipelines.
Okay, sir.
Thank
So we can conclude the discussion today because already 4:10, 4:05. So thank you very much for all the participants actively participating in this session. And I also very much thankful for our expert, Mr. Abdullah, for helping us answering the question and participation in the presentation. Thank you and have a nice day. We will be looking forward to meeting you in the next webinar, hopefully in the month of Ramadan. Thank you.